Question 5's a projectiles problem. We've got a small ball projected at a speed of 28, horizontal ground, moving for t seconds, passes through the point A. A, we're told, is 40 meters horizontally away and 20 meters vertically up from the origin 0, blah, blah, blah. Motion of the ball models a particle. Given that the ball is projected in angle alpha to the ground, use the model, show that t is equal to this. Okay, well, we've got most of the things written on the diagram. The two things I will add are the components of the speed here, horizontally and vertically. Okay, let's work on part A. Just as a sort of a little trick in a way, you can see that this answer contains cos alpha, and cos alpha is part of the horizontal speed, so it's an enormous clue just to use the horizontal motion, which of course will be constant velocity, to prove this equation is in fact correct. So horizontally, suvat, the distance is 40, the initial speed is 28 cos alpha, the final speed is 28 cos alpha, the acceleration is 0, and the time is big T. The equation that links that is S is equal to ut plus a half at squared, but A, remember, is 0. So we just get S is equal to ut. So therefore t is equal to S over u, which in our case is equal to 40, divided by the speed, which is 28 cos alpha. And if we take the factor of 4 out of the equation, we get that t is equal to 10 divided by 7 cos alpha, which is what we were asked to prove. So again, a small clue, given that the vertical speed is described in terms of sine alpha, we've got tan here, so this must include both the vertical and the horizontal speeds. So if we consider now the vertical motion to get from 0 to A, that will be an equation involving sine. We will mix that with our equation here for t, and hopefully we'll get what the question wants. So vertically, suvat, and let's choose that direction as positive. The positive change in displacement is a positive 20. The u is 28 sine alpha. The v is, we don't care. The acceleration is negative 9.8 meters per second squared, and the t is t. Again, the equation that links these variables will be S is equal to ut plus a half at squared. So let's substitute our values in and see what we get. 20 the displacement, here's ut, and this is a half a, 4.9 t squared. So if I now substitute the value for t that we got in part A, and if you'll forgive me, I will substitute that in and do a little bit of simplification, and you should get this, that 20 is equal to 40 tan alpha minus 10 sec squared alpha. So substituting one of the trig identities that you should know, I can transform the sec squared into a tan squared, and after a bit more simplification, I should get what the question wants. First of all, of course, we can cancel a factor of 10 out of this all, so what I get is that 2 is equal to, and that indeed does simplify to what the question wants, which is tan squared alpha minus 4 tan alpha plus 3 is equal to 0. And we've proved it as required. So I've moved part C across here to give myself a bit of room, and in part C we've been asked to find the height that the particle reaches at its maximum. Again, this is a suvat question, and the crucial point is that at the point of its greatest motion upwards, the vertical component of v is 0. The velocity momentarily goes to 0. So here's my suvat, and I've chosen again the vertical direction going upwards as positive. S is equal to question mark, that's going to be our answer. The u again is 28 sine alpha. V this time will be 0. The acceleration due to gravity is negative 9.8, and the t doesn't matter. Which equation links all this lot, which is v squared is equal to u squared plus 2as. And if you work that out and make s the subject, you'll get that s is equal to 28 sine alpha squared divided by 19.6. But the trouble is, we don't know alpha. But we can find alpha from solving this equation here, a quadratic in tan alpha. And if you factorize the quadratic, you will get that tan alpha minus 1 multiplied by tan alpha minus 3 equals 0. Solving these two possibilities, I get that alpha is equal to 45 degrees and alpha is equal to 71.5 degrees. So I've got a choice, and I'm going to choose that alpha is 71.5 and see what value that results. So if I substitute my alpha value into this guy here, I get that S is equal to 36 meters, which, judging by all the dimensions on the diagram, is a perfectly good answer. If you try 45 degrees as an option, you will get that S is equal to 20. And that clearly is a nonsense for the model, the same height as the position A. So we can reject 45 degrees as one of the solutions that we can disregard. Part D. So it's sort of a waffly question at the end. We're asked to state one other limitation of the model. Well, limitations of the model are the fact that gravity is not always constant and is not always 9.8 all over the globe. So we need a more accurate description of gravity on the particular location that we were doing this experiment. The other thing is that no projectile which is going to follow this sort of path can't be truly regarded as a particle. So I've written here that a particle is in reality not possible, and we need a better value of g for the acceleration due to gravity. And there we are.